You ever notice how some things in the world are just connected? Like the more hours you work, the more you earn. Or the faster you drive, the less time it takes to get somewhere. Well, math actually has a special language for describing these exact relationships. It's called variation, and today we're going to learn how to speak it. So let's dive in and decode the language of variation. This, right here, is the big question we're exploring. We're going to break down all the different ways that quantities can influence each other, and we'll turn these abstract ideas into some really simple, predictable formulas. So here's our game plan. We'll start with the main idea, then we'll look at direct and joint variation. After that, we'll tackle its opposite, inverse variation. Then we'll smash it all together. And finally, I'll give you a handy toolkit that you can use for pretty much anything. Okay, so in every single relationship we look at today, there's this secret ingredient. It's a number we call the constant of variation, or just K. Think of this number as the key that unlocks the specific connection between our quantities. Finding K is almost always our first move. Let's kick things off with the most intuitive type of relationship there is, when two things move in the same direction. You know, when one goes up, the other goes up, and when one goes down, the other one follows right along with it.
This is called direct variation, and the formula? It's beautifully simple. Y equals K times X. All this means is that Y is always a constant multiple of X. It's kind of like an hourly wage. Your pay, Y, varies directly with the hours you work, X, and your hourly rate, that's the constant, K.
All right, let's see how this actually works. We're told Y varies directly as X. So in our first scenario, Y is -3 when X is 24. Now the whole idea is that the ratio of Y to X is always that constant K. And if the ratio is constant, we can just set up a simple proportion. Y1 over X1 equals Y2 over X2. From there, we just plug in the numbers we know, do a little cross multiplication, and solve for our missing value, which in this case turns out to be 2. The key thing to remember is that the ratio between Y and X always stays exactly the same. Okay, now it's your turn to give it a shot. Using the problem right here on the screen, if X is 6 when Y is 32, what is X when Y equals 8? Go ahead and pause here to work it out. The process is exactly the same. Just set up that proportion and solve. So what happens if something depends on more than one other thing? Well, that's where joint variation comes into play. It's really just like direct variation, but now we're multiplying our K by 2 or more variables. For example, the area of a rectangle varies jointly with its length and its width. See? More than one thing. The logic here is exactly the same. We've just got an extra variable in the mix. Since Y varies jointly with X times and Z, our proportion now puts the product of X and Z down in the denominator. So Y1 over the product of X1 and Z1 equals Y2 over the product of X2 and Z2. We plug in our first set of values on the left, our second set on the right, solve for that missing piece, and we find our new Y is -30. Ready for another one? Let's apply that same logic. If A varies jointly as B and C, and we know one complete set of values, what is A in the second scenario? Again, just set up that proportion and see what you come up with. So far, everything's been moving in the same direction. But what about relationships that are, well, opposites? You know, when one thing goes up, the other goes down. Let's explore that right now. The difference is incredibly simple, but it's really powerful. With direct variation, remember, we multiply by X. With inverse variation, we divide by X. That one single change, from multiplication to division, that's what flips the entire relationship on its head. This is inverse variation. As one value gets bigger, the other one has to get smaller to keep their product, K, the same. A perfect real-world example is travel time. The faster your speed, X, the less time, Y, it takes to travel a fixed distance. They're opposites. So how do we solve these? Well, remember, the formula is Y equals K divided by X. If we just rearrange that a little bit, we get that K equals X times Y. And since K never ever changes, the product of our first pair of variables must equal the product of our second pair. So we set up M1 times N1 equals M2 times N2. We plug in our values, solve for the missing M, and we get our answer 2.4. All right, time to test your understanding of this whole inverse relationship thing. Given that F is 15 when G is 9, what's F when G is -6? Just remember the logic. The product of the first pair equals the product of the second. You got this. Okay, so we've learned the building blocks, right? Direct, joint, and inverse. Now, let's see what happens when we mix and match them to describe even more complex, real-world scenarios.
This is combined variation, and it's not really a new rule so much as a mashup of the rules we already know. A variable might be directly related to one thing, but inversely related to another, all at the exact same time. Let's break this sentence down piece by piece. A varies directly as B. Okay, that tells us B goes on top in the numerator. And inversely as C, that tells us C goes on the bottom in the denominator. And just like that, we've built our core equation. Now the process from here is two simple steps. First, use the complete set of data to solve for our constant k. Once we have k, we just plug it back into the equation with our second set of numbers and solve for that final missing piece, which is -8.
All right, here we go. The final challenge to put all your new skills to the test. Just remember the process. Translate the words into an equation. Use that first set of numbers to find k, and then use k to solve for the missing z. And there you have it. You've basically learned the entire language of variation. Let's do a super quick recap of the essential formulas that now make up your variation toolkit. This table right here is your ultimate cheat sheet. For directly, we multiply. For jointly, we multiply by more things. For inversely, we divide. And for combined, we just put the direct parts on top and the inverse parts on the bottom. It really is that systematic. So, I'll leave you with this question. How about the more you study for a test, the higher your score? That's direct. Or, the more people splitting a pizza, the smaller your slice. That's inverse. Now that you know the language of variation, you're going to start seeing these mathematical relationships everywhere. So, what will you notice first?